Okay, well, welcome to the first module, Practical Density Functional Theory. This is going to be in a way, it's a follow-on to what we had done last year. Could you raise your hand if you took or listened to a good portion of my density functional course last year? Okay, so there's a good group who did. I will, however, make this module fully self-consistent. And internally consistent, I should say. So you don't need to have had last year's module in order to understand this year's module. So it's completely independent from that point of view. But I won't have time, of course, to go over everything I did in a whole module before. So there will be certain points where I will not be justifying things theoretically. I'll have to refer you to the previous module. But I think you'll see that things will be quite plausible. And this will be a good starting off point. So as Erica just said, I'm the lecturer for this module. I'm Tomas Arias. There's a course website that I've set up. You can link to it either directly from the main course website. I think you've provided the link. Or if you can just remember tomasarias.com, you go to that and it'll forward you off to the website where you'll find, it's actually a Google Docs folder. And in there you have some courses I've taught in recent years, including this one. So then just click on the folder, 2011 Physics 7654, and you'll find all the basic course information and contact information up there, as well as the first assignment is already posted, and those sorts of things. Now, we also have a grader for the course. That's Ravi Shankar. He likes to be called Shankar. Sundararaman. Is he here? Is Shankar here? Yeah, there he is. He's in the back. He'll be the grader. Now, this course is going to be a little bit different from the traditional courses in terms of the assignments, in that there are no formal written out problem set assignments. This will be primarily a computational course, and so the assignments are basically to produce software that functions. So the grading load is fairly light for Ravi Shankar, but in exchange for that, he's agreed to hold some office hours to help you guys debug your programs. And he'll be having those Tuesdays and Thursdays from 10 to 11, we said, I believe, right? Right? And that'll be in 604 Clark. That's your guys' office? Yeah. Okay, very good. Okay, so all the contact info is up there. The first assignment, by the way, is already posted up there on the website. And it's due next Tuesday at midnight, just so we're clear what I mean. It has to be done before, basically, dawn on Wednesday. We'll see how it goes. Hopefully, we will cover enough of the material in this and the next lecture that would be a fair thing to do to you folks. The reason why I would encourage you, if you're taking the course, it's not absolutely required, but it will help a lot if you're following along with the assignments to complete them on time, is the goal, as Eric was alluding, is for us to be able to go down into the computer lab and then run and play with these codes in real time so we can explore various aspects of their numerical performance, and it can be kind of an educational experience, but that's not going to work too well if no one has a functioning code to pipe. So I'd like to encourage you to do that. I guess another issue is that I know there's probably at least one person in here, and there may be others from other departments who are interested in the practical aspects of density functional theory calculations, who maybe are coming from fields outside of physics, and so some of the other modules may not necessarily appeal to them. If you would like perhaps to get credit for this course, and you're coming from outside the department and you're just interested in this module, please contact me. I might be able to arrange like a special reading course or something for you. But if you're close enough in physics and you are interested in some of the other modules, as Eric says, please do sign up for the course. How many modules do they have to do?
Two.
So if there's one other, and I guess Cyrus is Monte Carlo, quantum Monte Carlo, it's another electronic structure method, so that might be a natural combination for anyone from whatever department. Okay. So I think that kind of covers the usual course administration stuff. I don't like to spend too much time on that. Let me just pause and ask if there are any questions on how the course is run and those things. All right, very good. All right, so here's the overview, or at least my current plan for today's lecture. We'll see how far we get. I want to begin by just describing to you what are the goals and the overview of the content of this particular module, so you can decide rationally if you want to proceed along with it. And then I'll dive right on into the material. As we'll see in the course goals, I'm emphasizing strongly in this course the benefits of what we call the Abinitio Approach. So I'll give you some idea of exactly what I mean by that. This will be some material people may have reheard from last year's course, but we have a good number of people who aren't in here, who weren't here last time. Then I'll introduce you to density functional theory. This is going to be on a need-to-know only basis, meaning I'm only going to tell you what you need to know. I'm not going to derive or prove the various theorems. But like I said, I'll make the overall framework, I think, quite physically plausible, and it'll give you a good grounding, a good starting point. I'll then jump right on into the main course material. And the main goal in the end, well, I'm transmitting this all already, but it's going to be to build up your own computer software from scratch to carry out density functional theory calculations. And what I'm going to do, I'm going to begin, though, stepping back and just talking in general a little bit about some good points of practice if you're going to apply computation to any kind of physics problem. Right? That's basically what we're doing here. So you get some general information on attacking any kind of physics problem computationally. I'll then spend a little time discussing what I like to call expressive software, which is in some sense more of a philosophy, really. And what this philosophy is going to allow us to do if we follow it is we're going to build up, as I said, you're going to build up your own density functional software in the course of about 4 weeks or so. Now, generally, this will take groups of researchers a couple of months to do. So how are we going to pull that off? Well, if you follow this expressive software philosophy I'm trying to advocate, you'll see that we'll be able to build up quite complex software quite rapidly. And I'll give you an idea of how that works. And I think it also works for a variety of other types of fields as well, if you generalize the concept. Finally, then, we'll dive right on into the first stage, the first sort of component of building up a density functional theory program, and that is being able to solve Poisson's equation. And I'm going to show you how, through this expressive software approach, we'll be able to solve that in a single line of code. Give you an idea of the power of the approach. So that's basically the plan for today. Any questions on the plan? No? All right, good. Hopefully the plan's clear. All right, so what are our goals here? An overview. I'm really, in this course, intertwining two different sets of goals. One set of goals is to introduce you to density functional theory as it is practiced. How do we actually get results out of density functional theory? And what that's going to allow us to do then, as I've been saying, is you're going to build from scratch, right from the beginning, your own software to make quantitative predictions of the properties of molecules and solids. Completely from first principles, in other words, ab initio. That's going to be the goal. So that's kind of fun. In addition to that, though, I have a couple of pedagogical things that I want to interweave. As I've been emphasizing, I want to show you good skills for any kind of a computational attack on a problem in physics. And of course, I'm going to be using this particular example of density functional theory as the foil, but you will learn a lot of good skills overall, regardless of what area might interest you. And finally, in doing this, we're going to necessarily learn a couple of good, powerful numerical methods as well. So it's like a mini numerical methods course in terms of we're going to learn, in particular, a lot about the practical applications of spectral methods in solving differential equations, and also methods for nonlinear optimization. So we're going to give you some good numerical methods, an overall way of attacking physics problems, and we're going to build up this software from scratch. So those are the goals. Question? All right. Okay, so what do we mean by the ab initio approach? The folks from last year have heard this, but it's still the best way I can think of to really summarize what it is that we want to accomplish. And the best way I have really over the years to come up with explaining the overall goals here of the ab initio approach is to take us back to the ancient Greek philosophers. All the way back some 25 centuries to he lived in Sicily, Empedocles. about 450 BC, I think it was. BCE, for being politically correct, I suppose. And he had a vision, a dream. Not a literal vision and dream, but something that he wanted to accomplish. And that was to be able to understand the material world around him through the power of human reason. Trying to go beyond, the sort of mythological view of the poets, but actually applying human reason to understand material experience. And he had a quite interesting view where, through thought and observation, he came to the conclusion that his material experience around him had to do with various combinations of 4 basic elements. Right? So he had 4 elements. And I think you guys probably remember what his 4 elements were. Can someone tell me? What did he have to make up all the material world around us? Right. Fire, earth. It's not earth, wind, and fire. Air, and water. 4 basic elements. And through all their various combinations, he tried to understand material experience around him. Not just to explain that there was a material experience, but to explain the various different materials as well. He had gone a little further than that. We usually hear about the 4 elements, but he also had 2 interactions. And he named those love and strife, by which modern historians of philosophy understand he must have meant attraction and repulsion. Those 2 basic interactions. Among these various elements and their combinations, and through these various interactions then that explain the material world, provided he followed a specific method. And that method, again, was to apply human reason dialogue and the basic methods of philosophy. That was some 25 centuries ago. And the amazing thing is that actually, only, I could say maybe in the last 15, 20 years, has this dream been achieved. We are living in the era where this has actually been accomplished. And that's what the Abinitio Approach really is all about. Where we can not only explain, but we can make the goal is to make quantitative predictions about specific materials and phenomena. The dream is the same. The description has changed a little bit. But in some senses, it is pretty close. So we actually have how many basic constituents of the material world around us? Or I should say, actually, I'll tip this off. There are 2 basic constituents needed to explain all of, all the material experiences that I've had, at least. What are those? There are 2 components, not 4. It's actually funny, because some of the Greek philosophers would then argue, well, actually, earth, fire, and water are all composed of air. I'm not talking about pointing down to 2 of those, but what are the 2 in our modern conception of the material world? What do we have? Or give me at least one. Electrons, right. So there are electrons. What else do we need? Sir? Nuclei, right. To understand our material experience, most of it, we're not talking about radioactive elements or something. We don't need to know about the quarks and the gluons and the protons and the neutrons. To predict material properties quantitatively to a very high degree of accuracy, you only need to consider the nuclei as indivisible point masses with charge corresponding to their atomic numbers. So there are 2 components instead of 4. But the fact that there are a finite number of components actually shows these guys weren't, so create interactions. Turns out that we only need 1 interaction. Of all the interactions that we know about, there's only 1 that we need to make predictions, again, of materials behavior to an accuracy of a few %. And that is just simply, does anyone know? I know the guys from last year do, but there's one interaction. And I'll give you a hint. It shows exactly the aspects that Empedocles had anticipated: attraction and repulsion. The Coulomb interaction. I find that just really amazing, actually, that all the, well, there's some subtleties with magnetism and so forth, but within a few percent, you can pretty much ignore those unless you're focusing on them. Predict all the material behavior around you. Coulomb interaction. Our method then is a little bit different from Empedocles, right? We employ the laws of quantum mechanics, which basically boils down to what we would like to do in our fantasies is solve the many-body Schrödinger equation. And Cyrus isn't here, right? That's really too hard, a direct approach on it. Although the quantum Monte Carlo module will show you how people get pretty close to it without making too many approximations. So there are still approximations involved. We will be focusing on using density functional theory, which was developed in recent decades, actually. And it's the combination of that development, which I guess won Walter Kohn the Nobel Prize in '99. I think it was 9. I should know this. And the advent of modern computational power is really what's made that really take off in the last couple of decades. So those are the methods that we are going to then be applying in this course. All right. So that's the Abinitio Approach. That's the tree. Now, what's next on my list here? Density functional theory. What you need to know about it. Well, first I'd like to give you some sense for how well it actually functions, how well it works, maybe as some kind of motivation. That it's a good approach to try to follow. I think this is the order I wanted to do it in. In the meantime, while I'm firing this up, any questions on the Abinitio approach? General philosophy? This is embarrassing, it says. Let's see, classes. I should have just gone to tomasarias.com. Come on. This was all preloaded. A basic training. Spring 2001. Public. Readings. Slides. First lecture. Oh, thanks. Yeah, I was just thinking that. Okay, view. Start presentation. That's pretty good. I'm a little afraid to hit F11. All right. Okay, so I'll be showing you in a couple minutes the basic density functional theory framework, but in the meantime I want to show you some examples of what we're able to calculate with it, and in particular how accurate it can actually be. How accurate can we get? So here's a first example of some calculations our group carried out on magnesium oxide, very simple salt type crystal. Here is the crystalline structure. And it's a long story, but this particular piece of research, we were working on developing a new kind of a basis set that allowed us to carry out these calculations to much more precision than had been done before, so that we could really try to get at the true accuracy of density functional theory apart from the various approximations, numerical approximations that go into the calculations. So what I'm showing you here then is a comparison of the experimental data for the lattice constant, the binding energy per chemical unit of the MgO crystal, and the bulk modulus, which is basically the spring constant against isotropic compression. And I'm showing you results which we calculated in two slightly different flavors of density functional theory. One is the local density approximation, one is the generalized gradient approximation, whatever. But let's just focus on the GGA. That one actually worked a little bit better here. And what you can see here is that we were able to predict completely from first principles with the theory I'll be writing down for you in a little while the lattice constant, and look how nicely that comes out. Whoop. Well, that's disturbing. All right, 4.22 instead of 4.21. That's pretty good. A small fraction of a percent error. The cohesive energy also came out quite nicely, about 1% off. And the spring constant also, good to within a few percent. Yes?
What's the error bar in the experiment?
That's a very good question. I believe the experiment is good to the significant figure shown. These experiments have a range of values in the literature, so give you a rough idea there. And this kind of gives you your first sense for how accurate density functional theory can be. It's usually good to within about 5%, I would say. Sometimes you do better, sometimes you do worse. Certain properties tend to be better. Lattice constants, as we see here, are usually good to within 1% or so. Cohesive energies, maybe a bit worse, maybe 10%. Moduli also maybe 10%. But overall, if you're just learning about density functional theory, keep it in the back of your head, about 5% accuracy for the theory we'll be writing down. We can do a lot more than just look at the properties of a bulk crystal. Here I'm looking at the phonon spectrum calculated in density functional theory. The calculations are the solid lines. This is a different group, actually. And the dots, I believe, are neutron scattering data. So again, within just a couple percent, you do amazingly well for a little bit of a more complicated property. Here we're looking at defects in a crystal. You don't have to just study perfect crystals. That's where a lot of the new techniques in computational power have really allowed us to study a broad range of phenomena. So in this case, what we're looking at is a defect in silicon known as a dye vacancy. You go into the crystal and you zap out two of the atoms. This is a common defect in crystalline silicon. Those are indicated here by these atoms in gray. And when you do that, the crystal then tends to deform around that